This is a fully functional 3D printed cultivation system designed to grow crops without using a single grain of soil. This image compares pepper plants grown under different conditions. Hand-watered soil on the right produced a 28-centimeter plant. Moving left, hydroponics reached 30 centimeters, while aeroponics achieved 40 centimeters. The data suggests that by removing soil and optimizing the delivery of nutrients, we can significantly increase biological output. Sustaining this growth requires solving a basic biological conflict. Roots fully submerged in water will suffocate and rot, but those left exposed to open air will quickly dehydrate and die. We can manage this balance using capillary action. This is the same physical force that allows a paper towel to absorb a spill. Narrow channels allow water molecules to climb upward against the pull of gravity, creating a wet surface while keeping vital oxygen pockets open and accessible. By utilizing this upward pull, we can engineer an environment that maintains an ultra-thin film of moisture across the root zone, ensuring the plant remains hydrated without losing access to oxygen. The hardware is comprised of 3 distinct 3D printed modules: a base reservoir, an outer Voronoi exoskeleton, and an internal gyroid core. These components must be printed using food-safe PETG filament. Standard PLA is not suitable for this application. PLA is biodegradable and will lose its structural integrity when exposed to constant moisture. When combined with the acidic salts found in liquid nutrients, a PLA structure will begin to leach chemicals into the water and eventually collapse. PETG remains stable and chemically inert in these conditions. This research paper details the finite element modeling of triply periodic minimal surface structures. This geometry provides maximum surface area in a small volume, acting as a structural substitute for soil, with thousands of physical anchor points for roots, without the density of dirt. By turning these mathematical models into physical prints, we create a specialized architecture that replicates the supportive functions of soil. To activate the system, we install a microfiber capillary wick. This threads from the reservoir's bottom up through the gyroid core's center. The wick must maintain continuous contact with the gyroid's internal walls. This allows the moisture to transfer into the surrounding plastic lattice through surface tension. Once the wick is positioned, slide the gyroid core into the Voronoi exoskeleton and mount the entire assembly onto the reservoir base. The Voronoi exoskeleton acts as a breathable structural cage. The open gaps allow air to circulate freely around the roots, which regulates internal humidity and prevents the growth of anaerobic mold. This modular design keeps the structural supports and the fluid delivery systems separate, ensuring that airflow and hydration do not interfere with each other. With the assembly complete, fill the reservoir with water and a 2-part hydroponic nutrient solution. These specialized nutrients are different from standard grocery store fertilizers. Soil-based fertilizers must be broken down by soil microbes before the plant can absorb them. Without soil to act as a buffer, the heavy salts in standard fertilizers will quickly crystallize. These crystals will block the microfiber wick and the pores of the gyroid, cutting off hydration and damaging the roots. To start the growth cycle, insert a sprouted seedling anchored in a rock wool cube into the top opening of the gyroid core. Within 2 weeks, the root system migrates. It grows out of the rock wool cube, following the moisture film embedded within the gyroid's geometric curves. By aligning the chemical ratios of the solution with the physical design of the core, we create a self-sustaining environment for the plant to mature. The result is a completed biocapillary system that operates indoors under a full-spectrum LED light. It provides hydration driven by basic physics, results in zero water waste, and ensures the roots have constant access to oxygen. While this passive version is effective, the next stage of development involves integrating digital monitoring. This sensor array, including a pH probe and an ultrasonic distance sensor, can be connected to an ESP32 microcontroller. This allows the system to monitor nutrient concentrations and water levels in real time. Integrating 3D printed geometries with capillary physics and environmental sensors allows us to manage every variable of plant growth through precise, measurable engineering.